Great, so welcome back. On the second part, we're going to discuss a little bit of the difficulties that some researchers found in order to convince the artificial intelligence community to adopt probabilities as a way of doing reasoning. Before touching this topic, I just want to say really briefly that probabilities have two different meanings. One is very concrete and objective, and we can interpret probabilities as frequencies that come from an experiment that we can repeat many times. And so the probability of each outcome is going to be the frequency that outcome appeared in a repeated experiment. But also there is a more subjective interpretation for experiments that we cannot repeat, right? So it will show up several times in our course. Frequently we think about probabilities. We ask, for instance, an expert, a physician, about what is the probability of a certain diagnosis, and that person do not rely directly on frequencies, but try to estimate that based on experience or based on some expectation that the person has. So you're going to be very subjective. So there is a lot of controversy about which interpretation should be used, and you may think that because we are calling degrees of belief, we are complying with the second interpretation. But that is not true. You see that for different problems, one interpretation comes more naturally than the other, and we adopt the interpretation that is more natural to each problem. Because independent of the interpretation, the techniques that we will develop in this course can be used for both, because both interpretations are governed by the same laws of probability. So the techniques will work equally well, independent of what is our view of probabilities. So it's interesting to think why we need these probabilistic graphical models, because probabilities have been around for centuries, at least 300 years. So why do you need those models in order to make probabilities work in artificial intelligence? And the answer is quite simple. It's because when the research in artificial intelligence started working with probabilities, they realized that they need to scale those techniques in order to make use of hundreds or maybe thousands of different variables they were interested in. So the scale of the artificial intelligence problems they were trying to work with at that time was much larger than everything that had been done before. So they needed to find some efficient ways to represent those probabilities, and also efficient algorithms that will work over that representation in order to give answers in a feasible time. So that was a challenge, and we will see that those challenges will reflect in this course. So we will be frequently concerned how we're going to represent the problem for this domain in a compact way, and how we're going to make inference and get answers to our queries in an efficient way. And it was a huge challenge for the time, because imagine at the time they started proposing those probabilistic graphical models, we already had available, including working industry, some expert systems that basically are these reasoning systems, right? So, and they were based on older techniques that were available at the time, some logic, some pseudo probabilities, some other techniques. They needed to show that working with probabilities and with probabilistic graphical models would be better than using the techniques they had at the time. So they had a series of challenges they faced, and they had to convince the entire community that it would work better than the techniques they had available. And they had a lot of criticism they had to deal with, right? So researching artificial intelligence, they started saying, for instance, look, we don't think using probabilities, right? If a human being can think, can take decisions, and do not use probabilities, it's a sort of a existence proof that we don't need these probabilities, because we can create a system that replicates the human thinking and create something that's intelligent and does not rely on probabilities. It sounds a little bit strange kind of argument, but at the time it was very strong, because those researchers really believed they should create something that was truly intelligent. So trying to replicate the human thinking, at least at some level of abstraction, was important for them. But some other arguments were a lot more pragmatic. And one of these arguments was something like, okay, working with probabilities can be very expensive in a computational way, because we need to work with a large number of variables. So just to make it a little bit more concrete, let's suppose that we have a large number of variables that we want to represent. So let's try to draw here that we have variables like x1, x2, until xn, and we want this compose our domain. And I will suppose that those variables are binary. So there's just 0 and 1s. And in order to represent the joint probability distribution, we have to specify the values for every possible assignment, for every possible combination of those variables. So we'll have like 0, 0, 0, 0, 0, 1, and 0, 1, 0, and you can imagine that this will go until we finish with all those variables and have all possible combinations. So in the early stage of artificial intelligence, people believed that we needed to make a representation for this joint probability distribution. And because as we have the joint probability distribution, we can compute any other distribution that we want, just eliminating variables. It's a simple operation based on summation that we can take out some variables and have smaller distributions, right? And that's the way of doing inference. So for instance, if I'm interested, for instance, in the probability of x1, I can compute that by eliminating x2, x3, x4, and so forth until I have just x1. And this elimination process that we call marginalization is a very simple process. It's actually summing the variables out, and we go see this process in details in a lecture in the future. But we can get not just the probability of x1, you can get probability of x1 and x2 together, or just probability of x2 or x3. All those probabilities are accessible from the joint distribution, the joint probability distribution. The problem is that in order to represent this table, this is a sort of a best case scenario, because we have only two possible values. You're going to be 2 to this elevated to n. So it will be a table with exponential size. It will be a huge table. Okay. And also, when we calculate the probabilities here, that's going to be the probability of x1 and x2 and until xn. When you calculate this probability here, you're going to be very small numbers because all those probabilities must sum to 1. And so these numbers are going to be like 2 times 10 elevated minus 5, and maybe 3.7 times 10 elevated to minus 8, and so on. So these are very small numbers. So you can figure it out, right? So if we had, and in the beginning of artificial intelligence, people started considering that it was the only way of working with probabilities. If we had to express the joint probability distribution, it will be a huge table. Imagine that you have like 100 variables. It will be exponential 2 elevated to 100. It will be a huge table. At the same time, those probabilities will be very tiny. It will be very difficult, for instance, to elicitate that from an expert. Imagine you asking a question, something like, what is the probability of the person having fever and cough and had, I don't know, a car crash in the last 5 years and had this and that and that and that, and you ask a question composed by this. What is the probability for all those events together? Imagine the physician answering the question, something like, oh, it's going to be like a 2.3 elevated to minus 20, something like this. It will be impossible to do that. So people were looking at this from this side. They said, well, that approach is not feasible, right? Both because the table will be huge, so it will not fit in the computer memory. It's one problem. So it's the compactness of the representation, but also the algorithm that will operate over this table will also be exponential. It will have an exponential running time, because if you have to sum values in this table, right, it doesn't matter, you have to scan the table. If the table has an exponential size, the time for you to scan the table will also be exponential. So at the end, you cannot fit that in memory, you cannot compute that in an efficient way. In addition, you cannot get that information from domain experts, because you cannot ask for them to know those probabilities of having so many conditions at the same time. So it looked very difficult to implement in practice. But the trick is that we don't need to represent the joint probability distribution. We can factorize and represent smaller distributions. And that is the key factor for these techniques to work. We can factorize and store smaller distributions and have algorithms that are efficient operating over the factorized representation. Let's take a look on that. So this guy, Judy Pearl, he's now retired, but he was a professor at University of California, Los Angeles, and he is the winner of the 2011 Turing Award. He was the man responsible for the introduction of probabilities in artificial intelligence in the 80s. He wrote a series of articles convincing the community that the use of probability was feasible. And also, he proposed the Bayesian networks and several algorithms to operate over the Bayesian networks in an efficient way. And this was a key contribution to change the entire community and convince several researchers to start using probabilities. We call it a second chance because we had a first attempt to use probabilities in the really early years of artificial intelligence, but later on in the 80s, Julia Pearl came with his ideas, and it showed that they could work, and they would work better than use non-monotonic logic, for instance. Right? So they started demonstrating in a series of articles that probability did not have the same issues that the researchers were having with older techniques they were attempting at that time. Let's, to introduce the idea of Bayesian networks, let's take a look in an example so we can make it a little bit more concrete. So I'm going to read that for you, and we're going to discuss that after reading. So we have a student called Drew who finished a final exam in physics class and received a B grade instead of A grade that he was expecting. So this is the process of Drew thinking about the problem. So let me first check, look at the grade of my physics class instead of some other class. It is indeed physics. Is it possible the professor made a mistake entering the grade? I don't think so. I have taken a few classes with him, and he has proven to be quite careful and thorough. Well, perhaps he did not grade my question 3, as I wrote the answer on the back of the page in the middle of a big mess. I think I will need to check with him on this. I just hope I did not miss question 4. It was somewhat difficult, and I'm not too sure about the answer there. Let me check with Jack on this, as he knows the material quite well. Oh, Jack seems to have gotten the same answer I got. I think it is question 3 after all. I would better see the professor soon to make sure he graded this one. So this is a sort of a reasoning process that Rio is going through. He's trying to understand why he got a B instead of an A. And there are two, actually more than two possible explanations, but there are two basic ones. That one is the professor did not grade his question 3, that is expressed here. And the second one is he missed question 4. In some way, he did not answer that correctly. And for the second one, the question 4, he has a friend that is Jack that seems to know the material quite well, and Jack can confirm if his question 4 is the same as he got. So if it's the same, we are more confident that the question 4 is correct. And he goes talk to Jack, and he sees that Jack confirmed that is the same question. So it seems the cause is question 3, right? But there are other factors too. There is a problem here that initially he was considering, he was not looking at the physics class, right? So you see that we call that a perception error. But he confirmed that it was really physics. And also there was a problem here, that is the professor entering the, making a mistake, and it was entering the grade. So it's expressed here, right? So there are several sources of uncertainty here, and we want to model this as a Bayesian network. As we go through this process, I will tell you that there is not right and wrongs here. Of course, some models are really bad and do not reflect the reality. So, okay, there are bads, there are wrongs, but there are many possibilities. One of them is illustrated here in this figure. The idea is that we take the main propositions that we have, so the main facts, and try to map them into nodes of a graph. So this is the structure of the Bayesian network, illustrated on the right here. So you see that the main sources of uncertainty are mapped here to what we call variables, right? So on the top here, we have Q3, question 3 graded. We don't not sure about that. Q4, question 4 correct. Here we have Jack confirming the answer. Here we have earned A, and here we have clerical error. Let's just stop here and thinking about this. And we have edges connecting those nodes. The way that we're going to connect those nodes can change. This is a representation of dependency between the variables, but it's very common that we use the edges with the meaning of direct causation. So if a variable A causes a variable B, so we're going to put an edge that comes from A, it goes to B. So that is what is going on here. Look at this earned A, this node here, right? You're going to have this variable being true, right? So we earn an A if we have both a question 3 graded and question 4 correct. And here on the bottom, we have a reported A that is the result of having an earned A and not having a clerical error. And finally, we're going to observe an A if we do not have a perception error. So we are actually looking at the physics class. So those edges will tell us what is the direct influence, the direct causation between the variables. And it doesn't need to be that way. Actually, if two variables are connected by an edge, it basically means that there is no independence between these two variables, so one will influence the other. But when we are building the Bayesian networks, it's very common to think about causality. And when we do that, at least in my opinion, the Bayesian networks, they become easier to understand, right? So you're going to see here that not every node is obvious, right? So usually when we have this causality structure, the nodes at the top are the nodes that we are most interested. So probably our queries will be related to those nodes. These are nodes that we cannot directly observe, but we are interested in that. So I'm really interested in understanding if my, or actually drills, but if the question 3 was graded and if the question 4 is correct or not. We have some middle nodes that are a little bit more difficult to figure out for many of the models. Also, when we are modeling the Bayesian networks or the probabilistic graphical models, it's very common that this is the most unclear part of the models. What are going to put in the middle? These sometimes we call those variables the hidden variables. Many of them we cannot observe. We are not interested in those variables, but they are important in order to build a sort of a logic for the problem. So we needed to build a chain of causality in this case in order to explain why I observed or why I did not observe an A in the system. So, and in the bottom, we have something that we can observe. In this case, that we can observe the A in the system, or we cannot observe the A in the system, and this will be the input that we're going to give to the Bayesian network in order to make a query, right? So it will be very common to ask a question in the form of a probabilistic query, something like, what is the probability of Q3 given that an observed an A? So we'll put it that way. Right? What is the probability of Q4 that I did not observe an A, or something like this? So we are asking about the probability of the nodes in the top of the Bayesian network given observations in the bottom. It doesn't need to be that way, but when we have this causality thing, this causality way of modeling, this is very common. It will appear several times. You see during the course, right? So, for instance, if we have a diagnosis system, on the top we could have the diseases. The diseases will cause a series of symptoms, and some of those symptoms we will observe. The symptoms will be on the bottom. The disease will be on the top. We observe the bottom nodes, and we are interested in answering queries about the top nodes. Right? That's very common. It doesn't need to be that way, but it's very common. And okay, but this is the structure, right? I don't expect you to fully understand this now, but you can understand that the Bayesian network is a graph. More than that, is a directed graph because the edges have a direction coming from the node that is causing to the node that is changed by the first one. And it has no cycles, right? We say that the Bayesian network is a DAG, is a directed acyclic graph. So there are no directed cycles. And this is a sort of a limitation. You may say, okay, I can imagine a few problems that the graph will have a cycle. What I do? I will say to you that in most of those domains, there is time involved. So you see that when the time is involved, we can use older techniques to have this to deal with those cycles. Or sometimes we can use undirected graphs. It's also a possibility. In this case, it will be Markov networks. You're going to see how they work in a future lecture. But in this case, there will be cycles. Okay, and we need to complete this graph with probabilities. And we see how we're going to do that. We basically have a local information. We're going to put one probability in each node, and we'll see how this goes. But for now, I think that's good. Good moment for us to have a break, stretch legs, grab a coffee, and I see you in the final video of this introduction.